Okay, so we're talking about the first and second derivative tests and how that helps us to find the relative maxes and mins of functions in AP calculus. Okay, so the first thing we're going to do here is define a critical number. Okay, so a critical number will be defined as the value where your first derivative is equal to 0. Okay, those are your critical numbers. Okay, so for graphically speaking, okay, right, if we had a polynomial, maybe it's going to be a cubic. The critical values would be here, right, at this point, and probably here, right, some random a and b, right? These are non-specific values because at both of these points, your slope of your tangent line is going to be 0. Okay, so those are your critical values. They're where the first derivative happens to be 0. So if you have an equation, you're going to take the first derivative, set it equal to 0, and then solve for x. Okay, those x values are your critical numbers. Okay, that's what's we're gonna be testing to see whether those are relative maxes or mins in a couple of minutes. But that's what a critical number is. It's where your first derivative happens to be 0, right? The slope of the tangent line to your graph is 0. So if f prime is 0 or undefined, then, okay, so potentially you have a max or a min if you have if the first derivative is 0. Okay, if the first derivative is positive, then your f function is increasing. Okay, if the first derivative is positive, your function is increasing. Like here, right, this would be a spot where your function is increasing. The y values are increasing on that interval. So the slope of that line, or the derivative, would be positive. Okay, similarly over here we have a slope that is positive, right? The y values are positive. Your f graph is increasing. So your first derivative would be positive. Okay, and then similarly, on the flip side, if your first derivative is negative, then your function is decreasing. The y values are decreasing on that interval. Maybe you can't see the green, so you can see the gray. Okay, so if your first derivative is negative, then your f function is decreasing. And if your first derivative is positive, then your f is increasing. Okay, these are all the things that our first derivative tells us, right? The things that we can test by using the first derivative. Is the function increasing? Is the function decreasing? Does the function have a relative max or a min? Okay, if the f prime changes from positive to negative, then you have a potential relative maximum. Okay, a relative maximum point, or a relative, right, an extrema. It might not be the biggest one, but it's relatively the biggest one. Or we could have a relative min if your first derivative changes from negative to positive. Okay, so notice here on this graph, right, the y values are changing from negative. So here we have a decreasing function and our slope is negative. And then over here on this side, we have an increasing function and our slope is positive. So if it changes from negative to positive, you probably have a minimum value. And if it changes from positive to negative, you're going to have a max. Okay, so these are some of the things that the first derivative can tell us about our function, and some of the things we can find by using the first derivative. So let's investigate this function, y equals x cubed minus 3x squared, and here is the graph of that function also. So let's take the first derivative. So y prime of this function, okay, it looks like these are both going to be power rules. We'll bring the 3 to the front and make it 3x squared is the derivative of x cubed, and minus 2 times 3 is 6x is the derivative of 3x squared. Okay, so let's take and set this equal to 0, right? The first derivative test says we need to set our derivative equal to 0 so we can find out where those signs would change, right? Where does your f have a potential relative max or min? Okay, so it looks like we can do some factoring. There's some common factors here. 3x squared and 6x have a common multiplier of 3x. Okay, leaving us with an x minus 2 in parentheses. Okay, so if we solve both of these, right, if we solve the set 3x equal to 0, that means x has to be 0. Okay, that checks out right here. Looks like we have a relative max when x is 0. Sure enough. And our other 0 comes when x minus 2 equals 0, so at x equals 2. Okay, and it looks like, sure enough, we do have a potential relative minimum there at positive 2. Okay, so when you take the first derivative, you are finding the place where your f function, where your function has zeros, right? A relative max or a relative min. Okay, so in AP Calculus, we're going to have to justify saying which one is which. Okay, so we can do that by using the second derivative, also by applying the second derivative test. So let's look at our first derivative. That was a function called 3x squared minus 6x. Okay, so let's take the second derivative of that. So y double prime is going to be 3 times 2, which is 6x to the first power minus 6. Okay, 6x minus 6. And if we set our second derivative equal to 0, we can find the x-coordinate that is going to be our point of inflection, or where the graph changes from concave down to concave up. Okay, and we can do this, of course, by making a nice sign analysis. Okay, we can always make a sign analysis using our critical point, which was 1 in this case, right? 1 is your critical point. And plugging in a number to the left of 1 and a number to the right of 1 and seeing if you get a positive value or a negative value. So if we plug in, say, 0 into our second derivative, 6 times 0 minus 6 is a negative value. And if you plug in a positive 2, we get 12 minus 6, which is 6, which is a positive value. Okay, so according to our second derivative test, right, the function is going to be concave down to the left of positive 1 and concave up to the right of positive 1. Okay, and this is what our second derivative test can tell us, which means we're going to have a point of inflection at 1, right, when x equals 1. So let's see if that kind of makes sense with what we were looking at in our graph. Okay, so we have a 0 at 0, right? That one looks pretty good. And we have a 0 at positive 2. That one looks pretty good. And then here, when x equals 1, is where our graph changes from concave down, right? It's concave down to this point. And then it becomes concave up after that. Okay, so these are some things we can learn about for using our first and second derivative tests. Okay, so your critical points are the x values that you get when you take a derivative and set it equal to 0. Now, if you wanted to know the y value, right, you would plug your x's back into your function, and then you could calculate exactly what that y value is. Okay, please don't just use the graph to calculate the y value. Okay, it might be the same or it might not be the same depending on how funky that graph is going to be. Okay, so these are the things that our first and second derivative tests tell us, is where we have critical points or the zeros of your function, and then where you have a point of inflection, or where it changes from concave up to concave down. So let's see if we can summarize some things about the second derivative. If the second derivative is 0, that means that f has a point of inflection. F has a point of inflection. If the second derivative is positive, then your graph is concave up, right? This is the graph of f. The graph of f is concave up if the second derivative is positive. And if it's negative, your graph of f is concave down. Okay? There's what concave up looks like, and here's concave down. And then what happens if your second derivative changes from positive to negative? That means you're probably changing from concave down to concave up, just like in our example. And if it changes from negative to positive, then it goes from concave up to concave down. Okay, so this would be the point where it changes. The point of inflection is where your graph changes from concave up to concave down, or from concave down to concave up. Okay, so that's what the second derivative can tell us about the graph of f. Okay, even if we don't have a graph, maybe it's going to be some type of a crazy trig thing or an exponential thing that we have no idea what it looks like. Okay, they won't always be polynomials, unfortunately. Okay, so you need to be able to do the math to be able to determine these intervals where things are changing. Okay, so those are the first and second derivative tests to finding relative maxes and mins in calculus. Let's look at some more examples. We want to find the x values, right? The x values for the points of inflection, okay, and the intervals where the graph is concave up or concave down. Okay, so what we're looking for is where the second derivative is equal to 0. Okay, that's what the second derivative tells us. Okay, if the second derivative is 0, that's where we're going to find your points of inflection. So we are going to take some derivatives. Okay, so our first one we have x to the fourth minus 4x cubed, a nice polynomial. So f prime is 4x cubed minus 12x squared. Fantastic. Okay, and then the second derivative, make sure that on your AP test, if this was an FRQ, you are writing down exactly what you are calculating. Okay, don't just let them believe that you know that 4x cubed minus 12x is some, label it. Make sure you're labeling it. This is f prime, this is the first derivative, and this is f double prime, the second derivative. 12x squared minus 24x. Okay, so there is your first and second derivative. Okay, most polynomials of power greater than 2 are twice differentiable. So we need to solve this and see what those critical values are. Okay, so we set our second derivative equal to 0, 12x squared minus 24x. Okay, it looks like both of these have a 12x in common, so I'm going to factor that out. Right, factor out the 12x from both of those two terms, leaving me with an 12x and an x minus 2. So it looks like we have two critical points. Okay, from the 12x we get a 0, and from the x minus 2 we get a 2. Okay, so this function has two points of inflection, potential points of inflection. Okay, these are the x values, so that's all we need to know. Okay, so let's check. Now we're going to make a little sign analysis of these values. So we have 0 as a potential, and we have 2. So we need to see whether the second derivative is positive, and the graph will be concave up, or negative, and the graph is concave down. Okay, these are the things that the second derivative tells us. So if we plug in a number like, oh, I don't know, -1 into your derivative, right, into here, so this term will be negative. 12 times -1 is negative. And this term will also be negative. So we're going to have a positive value to the left of 0. A negative times a negative is a positive. Okay, so what if we plug in +1? This will be a positive, and this will be a negative. So a positive times a negative is a negative, so negative between 0 and 2. And then pretty obvious, if we have a number bigger than 2, like 3, everything is going to be positive. Okay, so we have these three intervals when you do your sign analysis, right? The SIGN analysis is a positive or negative. So let's see, on the interval where it is going to be concave up. Concave up is where our second derivative is positive. So from negative infinity to 0, and from 2 to infinity, our function is going to be concave up on those two intervals. And similarly, our graph is going to be concave down on the interval from 0 to 2. Okay, and of course it says justify, so calculus wants you to say because the second derivative is less than 0, okay, that's what makes it concave down. And because the second derivative is positive, means you're going to be concave up. Okay, so whenever it says justify, we're going to use the second derivative's positivity, right? Positives are concave up and negatives are concave down for those intervals where the graphs are those ways. Okay, so not too bad. I think your brains can handle that. So let's see if our brains can handle this. Okay, so this one is not a polynomial. This is 2 times x times the function e to the x. Okay, so we're going to take the first derivative. We're going to have to use the product rule, right? So it's f is your x function and g is your e function. Okay, so we're going to use the product rule, and 2 is just an innocent bystander. So we'll put the 2 out front, and then take the derivative of x times e to the x. So the product rule says f prime times g plus f times g prime. Okay, so the derivative of x is 1 times our g function, which is e to the x, plus our f function, which is x, times the derivative of e to the x, which is itself, so e to the x, times, of course, 1 using the chain rule, right? We have to multiply by the derivative of your power, but the derivative of your power is just 1, so we don't actually have to multiply it. So let's do a little bit of cleaning up here. F prime is 2 e to the x plus x e to the x. Okay, it could probably be cleaner than that, right? I'm sure if this were a multiple choice section of the test, it would have you write it like this. Okay, because both of these terms have an e to the x in common. This is an e to the x, and this one also has one. They would probably factor this out to put it with the 2, and then leave you with a 1 plus x in parentheses. Okay, so there is the first derivative. Now let's take the derivative of that. Okay, so once again we have ourselves a chain rule where e to the x is your f function and 1 plus x is your g function. Okay? So the parentheses by itself is going to be considered its own function, the 1 plus x, that linear function. Okay, so 2... so f prime is e to the x times 1 plus x, that's g. So once again, this is f prime times g plus f g prime plus our f function, which is once again e to the x, times the derivative of 1 plus x, which is just 1. So how can we simplify this? Let's clean it up a little bit again. We have 2 e to the x plus x e to the x. Okay, if I were to distribute this into here, let's just do that real quick. Plus another e to the x. Okay, so how many e to the x's do I have? Yes, 2 of them. Right, here's one of them, here's another. So I have 2 e to the x's plus an x e to the x. And once again, calculus probably wants you to factor out this common term. 2 e to the x's times 2 plus x. Okay, so yes, kind of intense once in a while when it's not a polynomial. Okay, but it's nothing that your brain can't handle if you sit down and think about it for a minute. Okay, when you're taking these product rules, be very careful, right, to take the derivatives and to write them down. And the derivative of an exponential is just its exponential self. So now we need to set this equal to 0 and solve. So we have 2e to the x equals 0, or we have 2 plus x equals 0. Okay, well this one's kind of easy. We know x equals -2, but how about this one? Nope, let's divide both sides by 2. So e to the x equals 0. So what do we have to raise e to in order to get 0?
1.
E to the first power, that's e.
0.
E to the 0. Can we log this? Can we natural log both sides? We can. We can. So is there such thing as the natural log of 0? No, it's not, because the graph of 0, of course, has an asymptote at 0, and the graph grows forever. So this is not going to contribute an answer to our problem. Okay, so we're not going to get one from there. That's undefined. So our only point of inflection is going to occur at -2. Okay, it's going to occur at -2. So let's do our sign analysis from -2. Okay, do we have positive values or negative values? To the left of, what if we plug in -2 here? Nope, -3. So e to the -3, this is a positive value. Okay, how do we know it's positive? Because e to the -3rd is actually 1 over e to the +3rd. Okay, so it's just a fraction, it's not a negative value, times 2, so this is a positive, but 2 times plus -3 is a negative. So to the left of -2, our function is going to be negative. Okay, so if we plug in something to the right of -2, then this is going to be a positive value times a positive value, and we're going to have a positive value. Okay, so we have positives to the right of -2 and negatives to the left. So our function f is concave up on the interval from -2 to infinity, because our second derivative is positive. Okay, so there's the calculus analysis. And f is concave down on -infinity to -2 because the second derivative is negative. Okay, so calculus needs you to justify this, and you're simply using the rules of the second derivative test.